Hi, grade 10. So today we are going to look at specific heat capacity and what that means and how we do calculations in regards to dealing with specific heat capacity. So what is the idea of heat capacity? Well, if we think practically and think about something that you guys are very familiar with, if you were to, put a pail of water out and let it sit outside for a really long time, and you happen to be putting that pail beside a pool. Okay, well, after a couple hours, anybody could put one hand in that pail of water and one hand in that swimming pool, and you should obviously notice a difference in temperature. Okay, which one would be warmer is my question to you. Okay, well, the pail would be warmer, right? The swimming pool is going to be obviously a little cooler, and would be if obviously the pool is not being heated by a heater. But if you were to compare the two, the pail and the swimming pool, which one has a larger mass? Obviously, the swimming pool has a larger mass, and this has to deal with heat capacity. So, the water in the pail needs to be exposed to sunlight for a shorter amount of time in order to raise its temperature by 1 degree Celsius. Okay, and that is what I'm talking about, specific heat capacity. So that pail of water, the water specifically in it, has a specific heat capacity. How much heat is it going to absorb in order to increase that temperature by 1 degree? And that is something that can be measured and calculated, believe it or not. So when both kettles are switched on at the same time, okay, kettle A, kettle B, which one is going to take longer to boil? Well, I'm hoping you can tell me that kettle B is going to take longer. Okay, and this is because, kettle B has a larger mass of water in it. So it has what we call a higher heat capacity compared to kettle A. So a definition for you, this would be a good thing to write down. What is specific heat capacity? So specific heat capacity is the measure of the quantity of heat, aka how much energy it requires to raise the temperature of 1 gram of a substance 1 degree Celsius. Okay, and each substance that you look at actually has a different specific heat capacity. Sand has a quite low heat capacity. Glass, not overly high. Air is a little higher, but water actually has a very high specific heat capacity in comparison to these three. If you were to look at this graph and to zoom in a little bit, you could actually see a couple other substances comparison. You'll notice silver, copper, and aluminum are quite high, or they're really good at conducting heat. However, as we move across the graph, it doesn't have as large of a heat capacity. But for example, water, even fish, believe it or not, have a high specific heat capacity. It takes a lot longer for them to essentially heat up 1 degree Celsius because it needs more energy in order to do that heating up of 1 degree. So another practical application for you. On a hot day at a beach, if you had equal amount of sand and water compared right beside each other throughout the same day, which one's going to feel hot faster? Okay. Why? The land, aka the sand, is going to feel hotter sooner. Most of you guys know that. We touch hot sand, we run across it, and then we jump into the, or maybe not jump, run into the lake to cool our feet down if it is too hot. That is because sand has a lower specific heat capacity and water has a higher one. So sand takes less energy to heat up that 1 degree Celsius. So this would be another key piece to maybe write down. Okay. So high heat capacity means that it has high heat absorption. It easily, it requires a lot of heat to be absorbed. Low heat capacity means low heat absorption. Okay, so what does that mean in regards to calculations? Because we know, or if we haven't figured this out yet, physics is all about calculations and taking what we know about our common world and figuring out the mathematics behind it and how it all interconnects. So using specific heat capacity, this is our go-to formula. This is on the back of your periodic table. You will find it there, okay? And the units for it, okay, so there's a nice formula. The units are not included, of course. From what you can see, originally, it doesn't look like they're included in your periodic table, on the back of it at least. However, they are. The unit for specific heat capacity is joules, which is energy, and then divided by grams, which is your mass, and Celsius, which is your temperature, which means all three of these things right here, energy, mass, temperature, are involved in the calculating and figuring out the specific heat capacity. Okay, so you can actually even understand what specific heat capacity means based on the units alone. It's the energy required to raise 1 gram of a substance, hence the gram, the mass, by 1 degree Celsius. So gram, degree Celsius, and joules is energy. So liquid water has a specific heat capacity of 4.19 joules per gram degree Celsius. Solid water, aka ice, has a specific heat capacity of 2.00 joules per gram degree Celsius. You'll notice both water, but they are in different states, which means that the specific heat capacity does actually change. Okay, so we can actually, these are not something you have to memorize. These are on the back of your periodic table down at the very bottom in a box called constants. If you don't have your periodic table, I'm going to really recommend you print this off or you write these guys down right here. Okay, because you are constantly going to be using this and you have to pick the right one based on what the question is talking about in regards to state. Is it ice? Is it water vapor, aka steam? Or is it just liquid water? Because state impacts the specific heat capacity. We are, for the most part, going to be dealing with water questions. So it might be liquid, solid, or gas, but you will have to pick. If it deals with any other type of substance, it will give you the specific heat capacity. Okay, so formula time. So this is on the back of your periodic table. What each thing means, feel free to, if you want to, on the back of your periodic table with your formula, write this down. Okay, Q is your energy, or sometimes in the questions it can be referred to as heat. Okay. M, little m, and it has to be little m, is your mass, and it needs to be in grams, not kilograms. If it is in kilograms, you have to change it. Okay. Q, your energy needs to be in joules. If it's in kilojoules or K, J, kilojoules, what that means is that it's actually kilo means 1,000, So you'd actually have to convert this. You'd have to times by 1,000 to put it into joules. Okay. Now, that specific heat capacity I was just talking about on the last slide, the 4.19 and 2.00 and 2.02, that is a constant that is almost usually always given to you unless you're solving for it, or you find it on your periodic table, and that is the specific heat capacity. Okay, so we represent that with a little c. And then our last part of our formula is delta. That's what the triangle means, T, and it is a capital T. In physics, a little t is used for time, so big T is used for temperature. Okay, temperature is going to be in degrees Celsius, and so what the triangle means change in. It's a Greek letter for delta. Okay, but change in temperature, so you have to figure out the difference between the two. All right. So using it, what does this mean? So I have this one wrote out, typed already. What is the heat released in your hand if 500 grams of water, make sure you note what state we're dealing with. So it's water, so this is your liquid, okay, in a beaker that cools from 100 to 37 degrees. So what I usually suggest you do before you start doing all this calculation stuff, I usually do it on the left-hand side just for convenience. I will pick out what my question gives me so it's easier for me to figure out what I'm calculating. So my little m is 500 grams. My unit is supposed to be in grams, so that can stay. My C is, I'm dealing with water, so I'd have to look at my periodic table and find 4.19 joules per gram degrees Celsius. And then delta T is 100, it cools, so 100 to 37. So that is 63 degrees Celsius. So when I know all of these, I'm going to double check my question. It says, what is the heat? So this means I'm looking for Q. So Q is my question mark. That is what I'm solving for. So now we get to do the math behind it. So I always write my formula in physics. So there's my formula, step 1. It is much easier if you work your way down the page. Okay, so M is 500 grams. C is 4.19. Delta T is 63 degrees. Notice I show all of my work. This is what I would put in my calculator, and I would get this as my answer. Okay, which is where most of you will stop, but we have done a little lesson on significant digits, which need to apply in every single calculation question we do in physics. So sig digs, we are looking at the least significant, which means I'm dealing with 2 sig digs right here. Okay, 37, 1, 2. These guys are 3, so 2 sig digs, which means I can't round these away. I need to put it into scientific notation, which means I need a number between 1 and 9. So I'm going to move my decimal. 1, 2, 3, 4, 5, 1.3. There's my 2 significant digits. And I move my decimal 5 times. And it was a very large number, so it's positive 5 joules. And that is my answer. All right, example 2. So I am going to start out by picking out what I know. So it says, what mass of ice? So that means I am looking for M. So M is my question mark. If we start with 37.5 kilojoules of thermal energy, so this is my Q, 37.5 kilojoules. Now notice it's kilojoules, but according to our units, we need Q in joules. So kilo means 1,000. So there's 1,000 meters in a kilometer. So we are going to actually multiply this by 1,000 to change it into joules. So 37,500 joules. Okay. I like to do this right off the bat so that I don't forget about it and go and do my calculations incorrectly with the wrong units. Okay. It says when ice was warmed. So that means I'm looking at C. Well, which C am I going to pick? I'm going to pick the C, ice. So this is at the bottom of your periodic table, just 2.00 joules per gram degrees Celsius. And then it says the temperature was warmed from -20 to -5. So -5, warmed actually. Yeah, so final minus initial, and I get 15 degrees, 0.0 degrees Celsius. All right, so there are all my numbers to the left-hand side. So that means if I write my formula, I can now put my numbers in and solve for my unknown. All right, so what we're going to do, we're going to plug in our information that we know based on all of the numbers we've pulled from the question already. So Q is 37,500. So 37,500 joules equals to mass. We don't know, so I'm going to leave that as my M. My C is 2.00. And my delta T is 15 degrees Celsius. So I am going to do a little math to make things simple. I'm going to just multiply 2 times 15, simplify. So this is equal to 30. And I haven't done anything to this side, so I'm going to keep moving downwards. Now I need to get M on its own, so this is where our math skills come in. M is being multiplied by 30. The opposite of multiply by 30 is divide by 30. And if we do it to one side, we're going to do it to the other side. So M is equal to 37,500 divided by 30, and that should give you 1,250 grams. Now we always need to include our units. And then we do need to consider significant digits. So looking at our sig digs, I have 3 here, 3 here, 3 here. So I get an overall just a 3. I don't have to really think about this one. However, in my answer, I have 4, which means I need to, and I have no decimal here, so I can't round away to 3 significant digits. So that means I need to put this into scientific notation. Okay, so I need to move my decimal to get it between a number between 1 and 9. So I'm going to go 1, 2, 3. So 1.25. I've moved my decimal 3 times. And it is a big number, not a tiny decimal number, so it's to the power of 3 grams is equal to my mass. So there is my final answer for the mass of the ice. Next example that you could get. So example 3, I'm going to do the same thing that I did before with my other question. I'm going to pull out my information as I go. So 42.81 grams, that's mass. And it's in grams, so it is in the unit I like. Okay, it says water vapor. So this tells me that it is a gas or steam. So C, I look at my periodic table on the bottom of the back. It says C, steam. So it should be 2.02 joules per gram degrees Celsius. And then it says absorbed 688.4 joules of energy. So this is my Q. Okay. It is important you get familiar with the units and the terms so that you know what each number is going with what variable. So 688.4. It is in joules, so that means I get to leave it as is. And it asks for the temperature. So I'm looking for delta T in this question. So now knowing all my information, I write my formula. MC delta T. Okay. I put in my information I know. So Q is 688.4 joules. M is 42.81 grams times 2.02. And I don't know delta T. So I am going to simplify, multiply these guys together, and that should give me 86.4762. 88 delta T. 688. I haven't done anything to this side, so I'm just following my work through. This is being multiplied by T, so the opposite of multiply is divide. 86.4762 cancels out. Whatever I do to one side, I do to the other. 86. Okay. And 688.4 divided by this guy should give you 7.96057. And that is delta T. Now, I don't get to just keep my decimals like that. Significant digits. So go back to my question. I have 4 sig digs here. I have 4 sig digs here. I have only multiplied and divided, so I get 4 sig digs. So 1, 2, 3, 4. Which means 1, 2, 3, 4. This number right beside my last sig dig influences my rounding. So this becomes 7.961 degrees Celsius because the 5 makes the 0 go up. Okay, so there is my answer for delta T. So that's my change in temperature. Now, B asked me if the steam started at 114.2, okay, what is the temperature now? Well, it says it increased in temperature. So I started at 114.2. This was my change in, so plus 7.961. And I get 122.2. And now this is with sig digs. I've rounded. And the reason I've rounded to only 1 decimal is because when I'm adding and subtracting, my least accurate, which means my least number of decimals, only with adding and subtracting, is how I decide sig dig. So 1 decimal here means 1 decimal in my answer. So the temperature that it is now is 122.2 degrees Celsius. So to wrap up the review of everything I've just talked about. All right. Heat capacity depends on the mass of the object and the type of material. Okay. Mass is part of our formula, so that makes an impact. The larger the mass, the larger the heat capacity. Smaller mass, smaller heat capacity if you're comparing the same material. Now, material also makes a difference. Okay? Different materials have different heat capacities. That is something that you will always be given. That is your little C in our formula. Proof and point, how this works. We know that certain parts of our car get extremely hot in Medicine Hat when it's nice and sunny out, specifically the metal, but the plastic parts will always stay a bearable temperature. Reason being, type of material, mass of the object, deals with your heat capacity that it has within it. Okay? We can think about this even when we come to eating pizza. And now I really want pizza. When you take a pizza out of the oven, you know the sauce is always going to be extremely hot, and so is the cheese. And it is going to stay hot, okay, for a decent amount of time frame because they have a high specific heat capacity. However, the crust that you're holding on to isn't as hot as the cheese and the sauce because it has a lower heat capacity, and it cools down quicker. If you have any questions, ask away. Hope specific heat capacity makes sense, guys.